Dear students, let us continue our learning the course Automata Theory and Computability. This is the second session of the module 5. The appendix, that is security, the topics covered in this session. Myself, Dr. Suresh.d from the Department of Computer Science and Engineering of Canara Engineering College, Bantwal, Mangaluru. In the security applications, how this automata is useful. That is a discussion for the class for this session. In the modern world, that is the current world, security is an important feature of almost every system we use. That is, you start from the mobile phone to your home safety system. So everywhere, it is one of the most crucial issue which is there in the address. We protect the physical locations with locks or the alarms. So as we do with our home security system. There the locking or the alarming system which was introduced over there. Then next, the laptop or the computer what we use. We protect with the safe operating systems and sophisticated virus checkers. That is, there are many virus checking mechanisms are there. So those antivirus we used to install and they are used in securing our computer systems. And the operating systems we are going to use, that is operating system will provide the security features. Then we protect the sensitive communications by encrypting them. It is one of the trending areas in the area of data communication, that is your encryption and the decryption mechanisms. Again, it is one more subject what we have. So now the theory which is described in this session has been something to do with these techniques of security, securing the things. How the security systems can be designed using your automata concepts. What are the automata concepts we have learned? Your finite state machines, regular expressions, grammar. How we can use them, especially the finite state machines. How the finite state machines are useful in designing the security, in addressing the security over there. First, the physical security systems as the finite state machines. Let us imagine a conventional intrusion detection system security mechanism that was found in the most of the types of the buildings or houses or offices and the banks. Such systems can be modeled as in finite state machines. Some intrusion detection systems are complex. That is, they may divide the region that is being protected into the multiple zones. Then the state of each zone may be partially or completely independent of the states of the other zones. But we can easily see the essential structure of such systems by considering the simple finite state machine which is shown here. So now if you look at the security system which is designed over here, the inputs for this finite state machine. So if you observe over here, it is a finite state machine wherein one is our initial state or the start state, and the state number 5 and the 6, they are our accepting states. Fine. How the machine system will work? The inputs to this finite state machine are the user commands and timing events. The timing events like are turn on the system, disarm means turn off the system. That is, we on the system and we off the system. Fine. So you can see the commands over here. So we on the system and the disarm will off the system over there. Fine. So ARM stands for turning on the security system and disarm means turning off the security system. Query the status of the system, current status of the system. To get the current status of the system, we are using the query, it will be used over there. Reset the system. Open the door. Activate the glass break detector and 30 seconds wait for it elapse. The job of the mission is to detect an intrusion. So how the intrusion is detected? First we switch on the system, we open the door and we open up the glass break sensor mechanism. So whenever the things will happen, so if we open the door, again we close the system and again we wait over here. Or we wait for the 30 seconds over there to go to our final system. Fine. So this is how a conventional security system works. Fine. So now in this one, so the states are labeled that require an alarm as the accepting states. State 6 differs from the state 1 since it displays that the alarm has occurred since since the last time the system was reset, and it is not allow the system to be armed until a reset occurs. Fine. So if you look at the state number 6 over there, so until we reset, we can't go to our starting initial state. That is, it will wait for an explicit reset from the system. That is, if anything happened over there, we used to buzz an alarm. Then we will wait. We will wait at the state 6 till we manually come and reset the system. So that it's a normal conventional security system which is defined over here. A realistic system has many reset. If you go to the realistic system, there may be it may have many states over there. So one such example, for example, suppose that the alarm codes consist of the 4 digits over there. Then the single transition from state to 1 to 2 is actually a sequence of 4 transitions over there. One for each bit that may be typed in order to arm the system. Suppose, for example, the ARM code is a 4449, then we describe the code entering fragment of the system as shown over here. That is, I should get to go from state 1 to state 2. I need to get this code. That is, first is 9, second one, third one, and the fourth one. Once I get all the 9s over there, that is the 4 9s, then the system is reset and I will go to the state number 2. I will go to the state number 2. That is, I am going to that is a turn on the system. For turning on the system, that is the different codes. The 4 9s are used as a code for the example over here. This is one such a scenario of having the conventional security system. That is the physical security system. Then the next one, computer system safety. So now let us consider a complex computer system that it includes files that some users but not others have to access it. That is, I want to have a restricted access to the files. You take a bank database over there. So in the bank database, what happens? Not as an user, we are not allowed for the all the operations of the on the files of the users. But as a bank official, we can go for the having the higher number of operations are provided over there. So such an example, fine. That is, there are files which we need to restrict for some, and we need to give access for some. Fine. So such scenarios will be your building such a scenario is in a complex computer system. So example, it includes the process like a print paychecks that some users are allowed to run, but most are not. That is, printing the checks is nothing but your manager has a right, and the rest don't have the right to print the checks. Right? So the such scenarios where we need a higher level of safety is required over there. Now, is it decidable whether a system is in the safe state? That is, we are not into an infinite waiting over there. Fine. Suppose that let us assume a scenario over here. So we have the two resources and two individuals are waiting. People 1, people 2, resource 1 and the resource 2. So now what happens is he is having the resource 1 in his hand and he is waiting for the resource 2. So that person 2 having resource 2 in his hand and he is waiting for the resource 1. So until the resource 2 is freed from the people, that is the human 2, P1 can't complete. And until the resource 1 was released by person 1, P2 can't complete. That is, both are went into an infinite loop. It's a never ending scenario. So that is such a scenario, so they are not safe for the computer systems. That is, we need to decide whether the system is in a safe state or not. So such a scenario is fun. So will be your, these are the main threats to the safety of the machine. For example, if it is decidable, give the operations that are possible in the system. Whether an unauthorized user can acquire access to the paycheck printing system. The answer to this question depends on of course, on the operations that are allowed. First, to build the model of a protection status of a system, we use 3 kinds of entities over there. First one, subjects. These are the active agents, generally process or the users. Objects. Objects are the resources that the agent need to exploit. These could be files, process, devices, etc. So here you notice that processes can be viewed both as the subjects, that is entities capable of doing things, and the objects, that is entities that other entities may want to invoke. Then the next one, rights. Rights are the capabilities that agents may have with respect to the objects. Rights could include your read access, write access, delete access, or execute access for the files. Execute access for the files or the process, edit, compile, and execute access for a source code check or change access for n password file and so forth. These are the three basic kinds of the entities what we are going to use in the safety system, protection system. They are subjects. These subjects are nothing but active agents, and the objects and the rights. So now let us look at the one such a simple access control box. Now I have the process and the files over there. So process 1, E can execute, process 1 can execute process 3, along with that one, E is the owner of the process, that is the process 1, and E has the right to read. Fine. So now the process 2. So process 2 can execute, then he has the rights to read. Process 3, you can just execute the process 3, and along with that one he is the owner of the file 2. Fine. So that is the simple current protection system of the protection status of the system, which is described with the help of the access control matrix A. So which contains one row for each agent and one column for each protected object. So each cell of this matrix contains the set of rights that the agent possesses with respect to the object. That is, either he can read, write, execute, or own. He may be the owner of that process. Right? So such rights will be there in the column. The protection status of the system must be able to evolve along the system. So we will assume the existence of the following primitive operations for changing the access matrix. What are that one? The first one is create. Create subject X. Create a subject X. So what is the subject? Subject is an active agent which generally the processors are the users. So now that will record the existence of a new subject X, such as a new user or the new process. Then the next one, create object. Objects are the resources that the agents need to exploit. So now for creating the object, it will record the existence of the new agent, new object X, or such as a process or a file. Next one, destroy. Destroy is for deleting that subject which you have created. Destroy the object. Enter or into A of S, 0, which gives the subjects the rights, subjects the rights, subjects the right or with respect to the object O. Fine. For this object O, what are the rights which are given? What are the rights which are given? Right. So for the subject yes, what is the right which has been given over there? Then next, to delete that right. To delete the right, we are going to use this one. Fine. So that is either we are going to give the rights or we are going to delete the rights over there. Next, the commands which are allowed for constructing from these primitives, but not all such commands must be of the following restricted form. The commands may be. So we have the list over here. X1, X2, X3 over there. So where X will be an object we are going to take. Right? So if right 1 is in your matrix and right 2 is in your matrix, in the same way the right J will be in the matrix AJ. For the right 1, the operation 1, the right 2, operation 2, in the same way for the right n, operation n are allowed. Right? All users are not allowed with all the operations. If they possess a particular right, only then they are allowed with to carry out that operation, or else not. Right? So that is for each subject and the object, we are going to give the right. We are going to give the rights, it will be given over there. Right? So in other words, the command may check that the particular rights are present in selected cells of the access matrix. Selected cells of the access matrix. So if all conditions are met, then the operation sequence is executed. All the operations must be the primitive operations which are as defined above. So no additional test loops or branches are allowed. A parameters x1, x2 up to xn must each be bound to some subject or the some object. The rights R1, R2 up to Rj are the hard coded into the definition of the particular command. So now this is how the framework for the protection is defined. So now defining the protection framework to be a set of commands that have been defined as described above and that are available for modifying the access control box. Defining the protection system will be a pair. What is that pair? Initialization and the framework. Init is the initial configuration that is described by the access control matrix that contains various rights in its cells. Framework is a protection framework that describes the way in which the rights contained in the matrix can evolve as a result of system events. The question is the designing the protection framework. So when we go for designing a protection framework, our goal is typically to guarantee that certain subjects maintain control over certain rights to other objects. You can think on the admin and the user applications. So admin has all the rights, but user has a limited rights over there. So if you have the two roles over here, admin and the user, so admin has all the roles and he has all the rights, but if you take up the user may not have all the rights over there. Fine. So that is our goal is to guarantee that some subjects will maintain the control over the certain rights when compared to the certain objects. Fine. So if we give the access for all the access to all, then there is a chance that there may be a leak. The data you are going to lose. So that's why we need to limit some rights to some users. Fine. So we are not supposed to give the rights to all the users. We need to limit the accessing over there. The rights to be limited over there. Fine. So in those cases, now we will say that a right has a leaked if it is added to some control access matrix cell that did not already contain it. Fine. Suppose the user don't have a rights to create a database, but he is able to create that database. Or there is a video which is a patented one, and the user is not supposed to download it. He don't have a rights to download, but he is able to download it. So in those cases, we say that it is leaked. The things are leaked over there. Fine. That is, even though the rights are not given for that subject, he is able to get those contents. Then we say that the information is linked. Fine. So simple example, you can take up your examination point of view. So the VTU question paper, VTU published the question paper and it is not to be given before your exam starts. And you are able to download it prior to the exam. So now what happens? It is a clear cut indication of the leak over there. Fine. So such a scenario will be the leak status over there. Fine. That is, we will say that the protection system is safe with respect to some right if there is no sequence of command that could be executed if executed from the system's initial configuration, which may lead the data to be leaked over there. If your data is leaked, then we say that the system is unsafe. It is not safe. System is unsafe. The other users are able to get your data. Then we say that the system is not safe or the unsafe. Right? So now this definition of safety is probably too strong for most real-time applications over there. For the simple application, it's fine. If it is for the VTU applications, as I told earlier, if you are able to download your question paper prior to your exam, then the system is unsafe. They need to conduct a re-exam over there, which needs lot of manpower and monetary loss. Fine. So that's why now the system is said to be unsafe over there. So now we should make the system leak proof. We need to make the system leak proof over there. Fine. So now this definition of safety is probably too strong for the most real applications. For example, if a process creates a file, that will generally want to assign itself various rights to that file. That assignment of rights should not constitute the leakage. So we should ensure that one. That should not lead to the leakage over there. It may also choose to allocate some rights to the other processor. What it wants to be able to guarantee is that no further transfer of unauthorized rights will occur. Unauthorized rights will occur. That more narrow definition of the leakage can be described in our framework in a couple of ways, including the ability to ask about leakage from arbitrary point in the computation, that is after the file has been created and assigned initial rights, and the ability to exclude some objects. Fine. And those who are trusted from the matrix when leakage is evaluated. Fine. So you may see that there is, when we go for the antivirus scan also, there is an option for excluding some directories which we trust, Fine. So such case can be built up over there. So now, given a protection system, yes, with the initial configuration and the framework and the right or, is it decidable whether the system is safe with respect to the rights? That is the question. Fine. So you designed a system. In your system, you are given some rights. In your system, you are given some rights to the, there are some 10 individuals are there, and you are given some rights to the each individual. So now from the initial configuration in your framework, does the system is safe or not? So now that I need to decide. So it is similar to that of your decidability questions. Fine. So we should be in a position to say that my system is safe, or I should be in a position to say that my system is not safe. Fine. So now it turns out that if we impose an additional constraint on the form of the commands in the system, then the answer is yes. We are able to do that one. Fine. Define a protection framework to be a mono-operational if and only if the body of each command contains a single primitive operation. The safety questions for mono-operational protection systems is decidable. But such systems are very limited. For example, they do not allow the definition of a command by which subject create a file and then gives itself some set of rights to that file. So we must consider the question of decidability of the more general safety questions. Given an arbitrary protection system, S equal to initial configuration and the framework and a right or, so is it decidable whether a system is safe with respect to the R? So now the answer will be probably the no. So which we can prove by the reduction, that is by applying the mechanism of our Turing machine. That is, we are able to design a machine, the Turing machine, which halts on the epsilon. The proof that is presented was originally given and concerned with the protection and the security of the specific context of the operating system. The key idea is quite simple. It is possible to encode the configuration of an arbitrary Turing machine M as an access control matrix A. To do this, we require a set of rights as well. So one for each of the M's tape alphabet, then one for each state M. So these must be chosen so that there is no overlap in the names over there. So with the ones that corresponds to the tape alphabet symbols, and let QF be the right that corresponds to the M's halting states. Okay. That is, with an initial configuration and the given set of right, we should be in a position to say that the machine is in the safe state or not. Then the next question, does the M ever enters one of the halting states when started with an empty tape? Fine, that is a question again. That is, if the machine starts out representing M's initial configuration, then does a symbol corresponding to any halting state ever get inserted into the safety cell of A? Right? That is, has the halting state or not? And if it is halting state, whether the halting state is leaked. Halting state is leaked. Fine? That is the question. Fine? So now look at the one such a scenario over there. So let us start with this configuration. Now the state, we are in the state number Q5. The symbol which is under the state number Q5 is blank. That is, the machine M is in the state Q5, and we assume that it started on the blank just to the left of the beginning of the input. So there are 4 non-blank symbols which need to be examined for examined squares on the M tape. This configuration will be represented with the square access control matrices in this way. That is, S1 first will be the 4th, that will be your square box. Then the next one, it is the owner, and the S2 is the A. Then S2 on S3 will be the owner, and S3 is the B comma Q5, and owner B comma N. Right? So now here, every row So one row and one column for each tape square S that is non-black has been visited. So it primarily only its cells along a S major diagonal contain the writes. The cell A of I comma I contain the write that corresponds to the contents of the tape of square I. Since the read write head is on the square 3, is on the square 3 over there, that is our B. 3, A of 3 comma 3 as the right. A of 3 comma 3 is the right, that is a B comma Q5, you can look over here. In the 3 comma 3 we have a B comma Q5, that is the symbol under scanning is a B and the state is a Q5. State is a Q5. Fine. So that is the contains the right. Fine. Corresponding to the state Q5. The only other rights encode the sequential ownership among the squares of that tape. If Si immediately precedes Sj, then Si owns Sj. That is the meaning. Fine. So finally, a cell that corresponds to the rightmost non-blank or visited tape square contains the right end over there. Fine. So now let us go for the other scenarios over there. So now in the state 5, Q5 reading the B, M writes in A and moves to the left or the right. Fine. So for that we construct the command. How it will be done? If one, then, so if you are the owner, one means if one, you are the owner means, and you are there in the Q5 in A of x1, x2, and if you have a B in the x2 of x2, then what to do? Delete B from there, delete Q5 from there. Now the B you are going to replace with A, and the Q5 you are going to replace with the Q6. This is how we write the control maxes. This is how we write the access control maxes over there. Fine. So here we must construct one such command for each transition of M. We must also construct commands that corresponds to the special cases in which M tries to move of the tape to the left and in which the moves to the right to a previously unvisited blank tape square. This latter condition occurs whenever M tries to move right and the current tape square has the right end. So in those cases, appropriate command must first create a new object and a new subject corresponds to the new tape square. Now let us look at this scenario. Fine. So in the first blank, in the first place we are there in the blank. We have the blank, that is S1 on S1 blank, the state is Q0. The state is Q0. The simulation of the Turing machine M begins by encoding M's initial configuration as an access control matrix. Suppose that the M's initial configuration is shown in the figure. Then there are a few other details we must consider over here. That is, we are going to test whether the QF ever gets inserted into the A's computation. Then next, we must be sure that the QF is not in A in the initial configuration. And if M starts in QF, then we will first modify it so that it starts in the sum. New state, fine. So now let us look at the theorem which is presented over here. The language safety equal to S comma R, where S is safe with respect to the R. What is R? R are the rights. Is not in the D. Fine. So how to prove this one? To prove this one, we have a machine that is H on epsilon, the machine M, a Turing machine M also on the epsilon. Is less than safety and so safety is not in the D we have to prove. So now the proof is quite simple, that is make the necessary changes in the M first one. If M has more than one halting state, then add a new unique halting state QF and add the transition, take it from each original halting state to QF. If M starts in its halting state QF, then create a new start state that simply reads whatever the symbol is under the read write head and goes to the QF. So this is the initial adjustment. Fine. That is, if you have the multiple accepting states, if you have the multiple accepting or the halting states, what to do? You create a single one, call it as a QF. And from here on epsilon, you connect over here. So now these are no longer your accepting states. So these are no longer your accepting states. Fine. First case, that is your first step. Second step, if the machine starts at the accepting state, if it is a scenario, then you have to split into the two states. On epsilon, we can go over here. Right? The next one, building the system, that is construct a initial access control matrix A that corresponds to the m's initial configuration on the input epsilon. What to do on the initial epsilon. Then construct a set of commands as described that corresponds to the transition of m. Then return that sequence, return that s comma q. Fine. Here the rules is a reduction from infinity, that is h epsilon, to safety. If Oracle exists and decides safety, if means you have in safety, then your mission will be decides your language. Fine. And R and your null can be implemented as a Turing machine over there. And C is correct. Fine. That is, we are able to design a machine which will halt, and it may say that it is accepted or the rejected. Then the second case, it does not halt only. That is, QF will never appear on the sum cell of the A. Fine. Now it will C will be get rejected over there. That is, Oracle accepts, but your C is rejected over there. Fine. So that is, this will be regarding your safety. This is regarding your safety. There are two aspects are there in this safety mechanism. One is the physical aspects, and other one is the computer system safety. To ensure the computer system safety, we discussed on giving the rights to the subject and the object over there. So while giving the rights, we should be ensure that it won't leaked off. Right? That is the entities. That is the rights. Even though you don't have the rights, is able to access means your contents are leaked off. So we need to ensure those components. So that will be regarding the security applications which are designed using the finite set machines. The references for this video are taken from the textbook Eldridge Automata, Computability and Complexity, first edition, Pearson Education 2012-13. Thank you.